loads it's going to run. What are you making the power supply for? What's the voltage levels that's going to be required by the load, right? You understand. What current is going to be required or power is going to be required by the load. So that's the two things you would consider. And then after that, everything basically would be just, then what would be the next thing you would worry about? So you got a load, right? First of all, you're going to say, well, what is this power supply going to have to do, right? You understand? So when they designed this power supply right here, what did they design it for? For what? For this computer, right? You understand that? Now they might make their computers to run on the standard power supply, but that was the first thing they did, right? You understand? Then what do you got to choose next? Starts with a T. Very few power supplies that I know of run off 120, provide 100. Yeah, we would pick a transformer, right? That would be able to do what? Supply the voltage and the power required by the load, right? You understand that? Okay. So we choose transformer. And then what would be the next thing we would do? So just go right down the line. So we have the transformer. What comes next, guys, in our block diagram? Rectifier. Okay, so we'd have to choose diodes. We'd have to say, okay, we need a rectifier that can block, right? So we got two things we consider for diodes: is how much current can they handle when they're forward bias, and how much voltage they can block when they're what? Reverse bias. That makes sense. The next thing we would do would be what? What? Choose a filter. Try to choose the right capacitor that would do what? That would be able to run the load, right, between those humps on our output of our power supply. So that capacitor is actually literally running the load, right? You understand, between the what? Between the humps on the pulsating DC that we get out of a rectifier. And then the last thing we would choose would be what? Starts with an R. We choose the regulator, right? You understand? We made sure we need to get a regulator that can do what? That can handle what? The current required by the load, right? You understand? And be able to drop the difference between the unregulated and the regulated and not burn it up, right? You understand? So if I've got 15 volts over on this side of my regulator at 1 amp, and I got 5 volts on this side at 1 amp, right? You understand? Then my regulator is dropping 10 volts. 10 volts, right, at 1 amp would be what? Would be 10 watts that that regulator would have to dissipate. If it couldn't dissipate that, so if you tried to get 20 amps out of it, what's going to happen? It's going to burn it up, right? You understand that? So that would be the considerations we would have. One thing we didn't spend much time in. So we know our transformer has got to be able to provide more than we're going to do what? Then we're going to regulate it. So if I wanted a 12 volt supply, what size transformer would we probably use? Nobody got any idea? Would I use a 12 volt transformer to get 12 volts DC? I'm sure there is. Probably 12.6. They've been around quite a while. So would a 12.6 volt transformer be able to supply a 12 volt load? DC load. Well, the bigger you make the transformer, the more your regulator is going to have to drop, right? You understand? So I go out and buy a 30 volt center tap transformer, 30 volt transformer, right? Okay, and I got a 5 volt supply. Well, that's going to wipe that 5 volt supply out, because now my regulator's got to drop all that voltage at that current, right? You understand? So what we're trying to do is trying to get one as low as we possibly can and still have enough to regulate at the current that we want to regulate, right? You understand? So if I want a 12 volt supply, then would a 12.6 transformer work? You say what? You say hope so? Let's do the math, right? You understand? So I'd come up here and I'd say, okay, that'd be 12.6, right? And then I'm going to come up there and do what? Now because my power supply is not looking at RMS, my power supply is looking at V peak, right? You understand that? So first thing I would do is I'd say, okay, what would that be? Yeah, I'd divide that by 707, 0.707. So that means my peaks are going to be almost 18 volts, right? You understand? So I got 18 volts of peak. Now, of course, if I don't filter it, then we wouldn't have enough voltage, right? And my regulator wouldn't work. So, okay, I got 17.8 volts, which is what my capacitor is going to choose up to. Of course, what we would do is we would come in and we'd say, okay, if I'm going to use a full wave bridge, then I would come up here and I would subtract what? I would subtract 1.4 volts. So that's what we have to work over with, 16, which looks like it's pretty good for a 12 volt supply, right? That's only 12 volts between what I need to do. But what we got to understand is that that 16 volts is peak, right? Y'all understand that? So what we're going to do, of course, is we got to come over here and say, okay, what did we say? I had 16 point what? Okay, so 16.4 or 16 volts. But if I full wave rectify, I got this, right? You understand? My regulator won't handle that. So what are we going to do with it? We're going to filter. Okay, so now what we got to do is we got to keep these pulses from getting down into my regulator. So we come up here and we filter this, then we're going to come up and we're going to end up with something like that, right? You understand? But if it's a 12 volt regulator, if these valleys right here drop below 12 volts, then our regulator can't regulate, right? Because what we'll end up on our DC is we'll end up with something like this. And we don't want that to happen. So what determines the size of that slope right there? V ripple peak to peak equals what? I of the load, what we want to do, divided by what? Frequency times what? Times the size of the capacitor. Okay. So I know what type of load I want. So what do we want our power supply to give us? No, but what current? What current do we want to design this power supply around? Let's say we want to make it a 2 amp supply. Okay, a 2 amp supply. Okay, it's going to be full wave. That's going to be 120 hertz. I know two things, right? You understand? So I know I can afford a ripple. So if we're going to regulate at 12, we don't want this thing to ever drop down below what? 12, right? You understand? So of course we would give us some safety right there. So let's say we don't ever want it to drop below 12. We got 16 volts, right? Right? Minus 12. That would allow us a V ripple peak to peak of 4 volts. Are we okay? Okay. So we'll probably come up here and maybe half this. So let's say it gives us a V ripple peak to peak because we want a safety margin, right? So I know my V ripple peak to peak, I'm going to do 2 volts. So what I did was half this, right? 2 volts peak to peak. I know what the current is. I know what the frequency is. So what can we solve for now? We can solve for the size of the capacitor that would handle this, right? You understand? So let's rearrange the formula and solve for C. So all we have to do, if it's on the bottom here on the top there, is just swap them, right? So I'm gonna say 2 divided by 120, right? Times 2. So 240. And this is going to give us our size of our capacitor in microfarads, right? You need to convert that to microfarads. You're going to get a fraction. And it's going to be a pretty big guy, right? So now I've sized my capacitor. Right? Does that make sense? Everybody okay? So y'all doing engineering work. We're just doing it with basically what? Math, and it's not hard math. So what size capacitor we got? What's that? It's going to be a fraction, definitely. 2 divided by 240. Okay, give me the fraction. 0.0, give me that fraction. 0.0083. So that would be 8.3 microfarads. Because I bet this is this would be 1, 2, 3, 1, 2, 3. So it'd be, right, 83, it'd be 8.3 microfarads, right? And then what would we do? There's no such thing as an 8,300 microfarad capacitor, so we'd always go what? Up. To at least the next standard value. So 10,000 microfarad. I'm sorry. Yeah. 10,000 microfarad. Now we got our capacitor. So this is the one that we hadn't talked about much. But that's the big guy, right? Because what's that doing is preventing that slope from getting into the water. So notice I took my V ripple peak to peak and I halved it, right? That gives us a nice safety margin. So now we can round our capacitor up one size and we'll be fine. If I tried to get 3 amps out of it, then we're out of the design for the power supply, right? And it's going to go out of regulation. So that's one thing you got to really consider is how much current you're going to need for your load. If you try to get more current out of it, you're going to do one of two things. You're going to go out, your regulator is going to go out of regulation or what, or it's going to burn out. So now I need a power supply that's going to drop my regulator. We'll use VP because that's what we're trying to achieve, right? You understand?
So are you going to always want to have it? So if you took 16 minus 12, you have 4. You always want to have that every time?
Yeah, so we're saying we could stand 4 peak to peak, but we want a safety margin built into it. So if I calculate a capacitor that will give me 2 volts peak to peak, then it's not going to get down into the regulator, right? So we've got a safety margin of 50%, right? Does that make sense? And then we can choose our capacitor and round up to the next size, and then we're going to be okay, right? Because the bigger the capacitor you choose, I could put a 100,000 microfarad capacitor in there, or I could put a 10,000 microfarad capacitor in there. One of them would probably cost me $50. The other might cost $5, right? You understand? So yeah, we could always go up extremely high, right? You understand? But we don't need to do that. So what we're trying to do is get our capacitor as low as we can possibly get it at what?
Still guarantee regulation.
So how much power would our regulator have to dissipate? So we'd say 16, right? What are we, minus 12, it's gonna have to do what? 4 times 2 would be at least 8 watts. We'd probably double that. Well, the only thing that we didn't work out that was on the how to calculate that. So what's C equal to? Your V ripple peak to peak, right? You understand? Divided by 120 times your current. I'm sorry. Huh? Yeah, C would be equal to I the load, right? Over the frequency of my pulses times the V ripple peak peak. So I think that's the formula I put on the review sheet, right? I don't know. So you just design your own power supply.
So we take the I load over the frequency times the capacitor, it gives VRPP, and it's going to be 2.
Well, no, what I did is it should, right? You understand? But what we're doing is we're trying to choose the size of the capacitor. So what we do is we come up with a V ripple peak to peak that we can handle and still maintain regulation, right? You understand? So we knew it was getting 16 volts peak, right? And so we said, okay, we're regulating 12. What's the difference between 16 and 12? That would put our value right here, which would be exactly at 12. But we don't want to put our value at 12 when our regulator is regulating at 12, right? So what did we do? We had it. So that gives us a 50% safety margin on our load, right? You understand? So that makes sense. A lot of people get your capacity. But the bigger the capacitor you choose, the more expensive it's going to be. If you're ever into the problem we have with big power amps in a car, where do they usually mount the power amp at? Anybody got in that? He's mounted in the trunk. So your stereo and your speakers up here in your cab, and your dang power amp is back in your trunk, right? And you got a 1,000-watt amp. 1,000 watts at 12 volts is a lot of current, right? And you're trying to get wire back there, and what's going to happen? Well, your wire is going to cause it to drop. So they put these big filter capacitors back there. And give them suckers, they pay $100, $150 for those capacitors because they got to be what? So big. Because they got to handle 1,000 watts of power between those pulses. So you have people run those cables, power cables, all the way back to their trunk, and they got to be big gauge wire, right? Well, you can't use extremely big gauge wire because you still got to get it back to your trunk, right? So they'll use filter capacitors. Yeah, I recommend they put batteries. You have a big old battery back there. Of course, batteries cost a lot of money too, but And then you got to consider 1,000 watt output. It depends on the efficiency of the amplifier. So you need to check, because there's no amplifier, there's nothing that's 100% efficient, right? Y'all understand that? So that means if I get 1,000 watts out, I probably got to put at least 1,500 watts into it, and that's what your power in your system. I've seen people run separate batteries and alternators just for their stereo. So they'll have a second alternator on their car running their stereo, and they'll have another set of batteries running their stereo, because your regular system can't do what? Can't handle 1,000 watts of power. Yeah. So y'all guys okay? Pretty neat, right? So everybody needs to go home and design your own power supply, right? 12 volts, that's a good power supply to do, so you could run anything you get out of a car. Because it's designed around 12 to around 15. Usually it's designed around about 10 to 15 volts. You should be okay. And then a variable power supply, I'll show y'all later on when we get into transistors and stuff, how we could actually get a lot of current out of these little regulators. We need to get to something that can give us a current gain, right? And what gives us a current gain? Transistors, right? So we'll get into transistors next. Anything else on there you want to look at, since I'm being generous today?
Review. It says, falling down data sheet term.
Yeah.
You got VRMM.
Yeah, that's what the data sheet calls it. Unfortunately, books, and we talked about this in class, books call it peak inverse voltage, which is the breakover voltage. Data sheets calls it VRRM, repetitive maximum. I'll have to look at it. So if we come over and look at the data sheet, and you're sitting over here looking for PIV, you're not going to want. You're not going to find it. So if we look at all these transistor data sheets that we have available to us, we're gonna deal a lot with the 3904, which is a NPN transistor. And then we come over here and we start looking for PIV. Guess what? Yeah, we can't find it. In fact, this don't even use VRRM. This uses VCEO. Oh, but we're looking at diodes. I'm sorry. Transistors call it that. So we're looking at diodes. We're not in transistors yet. Sorry, guys. So we look over here. Let me blow this up for y'all. Yeah, VRRM, VRWM, VR.
I seen the VRM, but you got VRM. Is that the same thing?
It's VRRM, I'm sorry. Yeah. This is the peak repetitive reverse voltage, and that's, so I need to go back and correct that. Because I added it on the review because I realized it was called, the book calls it PIV, right? You understand? But unfortunately, if you look for the PIV rating on these diodes, you're not going to find it. So I'll correct that. Thank you. But what allows us to get this charge these capacitors is this guy right here, this IFSM. This guy's rated at 1 amp, but it can handle 30 amps, right? non-repetitive surge current. So what this does is this allows us, you've got to understand a capacitor, when the capacitor is discharged, it's almost like a short circuit, right? You understand that? So what this allows us to do is charge those capacitors the first time, and then after that, it's looking at that slope, right? You understand? It's discharging through the load. It's charging through the transformer and discharging through the load. So this guy here can handle a surge current of what? 30 amps. It's non-repetitive, right? You understand? So I can't, if I tried to make it conduct 30 amps, it would burn up, right? And transistors have the same rating, but they call it something a little different. Since they have P-N junctions, if we reverse bias it, if we exceed the breakover voltage, then what's going to happen? It's going to avalanche and it's going to be destroyed, right? If we don't protect it with something. Okay, any more? So let me make that correction right now while I'm thinking about it. Okay, guys, then let's go to lab. Y'all working on